Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is problem solving for hydraulic modification. So, in this problem solving, what we understand, what are the various hydraulic modification techniques which we are going to include for better understanding about the various techniques in practical ways. So in this, we are going to understand these kind of modifications. What kind of modification is required as per the project requirement. It depends upon the project requirement. So as per the project requirement, we are going to choose the adopted technique. How we are going to choose that technique or choice of the method for getting that soil desired properties. So it depends upon the what kind of soil it is, what kind of environment is there, so which is suitable for that project requirement. These are all the parameters which we are going to understand in our whenever we are going to choose this technique. So this is the thing which we are going to follow. In this, we are going to understand what are the things involved. So in this, what we understand as a hydraulic modification technique, here we are doing the hydraulic point of view. What kind of requirement is required? It is nothing but hydraulic, it's nothing but the water. So here we are understanding the how the groundwater level, what kind of the water level it is there, what is the movement is there in that. So these are all the parameters which we are going to include in this kind of technique. So in this, what we will see one kind of problem statement here, that is design a well point dewatering system to lower the groundwater table by 3 meters. Over an area of 1000 square meters. So here the soil permeability is 1 into 10 to the power of minus 5 meters per second. So this is the problem statement how we have solved. So here in hydraulic modification, in most of the technique which we use, that is dewatering system. In that again different methods are we are going to follow as per the desired modification what we required. So here we are going to understand the problem statement. So here what is there? It is we are going to design a well point system that we know. So as per scenarios, and finally we know we are going to design well point dewatering system to lower the groundwater table. Here also we may understand it means well points dewatering system is nothing but it is going to change the water table level over and the required permissible area based on the surface area. So according to that, we have to, for this, we have to know the soil permeability. In some conditions, they mention if we don't know also, we'll go through the site and we'll take the soil sample. We are going to find out the permeability of that particular soil. These are the things which we are going to understand. So in this, the first thing as a solution for this problem statement, determine the required flow rate. So we are going to determine the required flow rate, lowering the groundwater table 3 meters, area to be dewatered that is equal to 1000 meters square, permeability of soil K is equal to 1 into 10 to the power of minus 5 meters per second. These are the things which we are going to understand. Those are required the flow rate. Here we are using the Darcy's law for find out the flow rate. First, we have to understand how the system is there, the flow of the groundwater table, how it flows, the movement we are going to understand. Before that, first we have to find out the discharge for that. So, for finding the discharge for these particular condition, we are using this Darcy's law. So, in this discharge, Q is equal to formula is K into area and the thing. So this is the how the level, how much we are going to change that level. This indicates the changing. So change of level, height, that is nothing but the change of level, and depth of the flow path. How much depth within the flow path is there. So like this we are going to understand the things. So here that was not mentioned. So if it is mentioned, if not mentioned also no problem. If it is mentioned, we will do as per that. Here if it is not mentioned, that's why we assume that is in 3 meters. So now find out the discharge. So we are applying all the things, permeability of the soil and area, that all this is already mentioned. In sometimes they give length and breadth or breadth and depth. As per that we are going to find out the, based on the given dimensions, we are going to find out the form area according to the dimensions. So here already they mentioned that is equal to 1000 3 by 3. It may vary. How much depth of the flow path is there, it is different. May lowering the level also they may vary in sometimes. So this is the discharge value. So 0.01 meter cube per second is the discharge value. So this is the way we are going to find out this required flow rate. So once we find out the flow rate, we are going to find out the how many number of well points are required. So we are assume according to the why, because it is assumed because of the depth of the flow is not mentioned in our problem statement. That's why we consider, sometimes it may 5 meters, it may 4 meters, it depends upon the practical scenario. So here number of well points, assume each well point can handle a flow rate of 0.01 meter cube per second. So here we got the discharge is 0.01 meter cube per second. So now we assumed the each. So we don't know in the complete detailing. So what is the required things, which kind of well points we are going to construct there. These are all the parameters for handling each well point condition. Here that was not mentioned. That's why simply we assume this is the each flow rate is maybe we may consider. So now number of well points is nothing but the how much total flow rate or flow rate of that particular condition, flow rate divided by each well point flow rate. That gives the how many number of required wells are required. So according to this is the 0.01 is the overall discharge, that is the flow rate, and divided by the what we assume each well point is going to handle how much flow rate. So according to this we require 10 well points. So like this we are going to understand the what kind of different techniques and terminology, how we are going to solve the problems as per the hydraulic ground modifications. So using this dewatering technique, using this well point technique. So that is the process according to the problem statement. Now one more kind of electro-osmosis dewatering. Calculate the current required for electro-osmosis dewatering of clay layer with a length of 50 meters and a cross-sectional area of 1 meter square. The electro-osmotic permeability is 1 into 10 to the power of -9 meters per meter square, and the voltage applied is 50 volts. So in this, according to this, using this also we mention the electro-osmosis dewatering. In some of the cases they may not be mentioned which kind of dewatering technique is adopted. So we follow the rules as per we follow the procedure, and which kind, what type of soil it is, what are the required things for the project. We keep it in our mind. We are choosing the required technique for getting the better results, for the better outcomes for that particular project. So here electro-osmosis dewatering of a clay layer is a clay layer with a length of 50 meters. So now the first thing which we are going to understand, that is equal to, we are going to find out the flow rate for this electro-osmotic flow rate, and after that we are going to calculate the how much, according to this we are going to how much applied current is there. So like that we are going to understand the calculations. Now in this, discharge is equal to the electro-osmotic permeability and area, and also the effect what we are going to understand in this. So in this, how much voltage per length, this voltage per length. So now it is for the electrical current. So now we are going to apply all the numerical values. Finally, we will get discharge is equal to 1 into 10 to the power of minus 9 meter cube per second. So now we are going to calculate how much it is using, that is equal to Q by K, that is equal to 1 into 10 to the power of 9 by 1 into 10 to the power of 9 multiplied by 50, that is equal to 50 into 50A. So this is the calculation which we follow for this electro-osmosis dewatering. In electrokinetic dewatering design, so this is also another technique which we are going to follow for understanding the dewatering system. So in this design a electro dewatering system for a 20 into 20 meters clayey soil area with a depth of 5 meters. Here the clayey soil area is 20 meters into 20 meters length into breadth, and the depth of that thing where we are doing all these the electrokinetic dewatering system design, that is the 5 meters. The soil has the electrokinetic permeability that is equal to 2 into 10 to the power of minus 9 meter square per volt per second, and also the voltage applied is equal to 1000 watts. How much voltage we are applied, that is equal to 1000 watts. These are the given parameters. As per the requirement, we are going to find out the first thing, that is the volume of the soil. Here volume is equal to area into depth. So area already, that is equal to 20 into 20 length into breadth into depth, that is equal to 2000 meter cube, volume of the soil. This is the volume of the soil. Now the next step we are going to follow, that is equal to flow rate. So according to the electrokinetic dewatering, we are finding the this discharge or flow rate. Flow rate is equal to, so this kinematic permeability value multiplied by area into voltage per depth. How much voltage per depth, that is equal to E. So applying all the numerical values into the respective parameters, so we will get this E is equal to voltage per depth. So the overall voltage is equal to 100. How much we are applied, that is 100 by depth is equal to 5, 20 volts per meter. So now we substitute this value into this flow rate. So Q is equal to 2 into 10 to the power of minus 9 meter square per second, volts per second, multiplied by area, that is equal to 2000 meter cube, and also the voltage per depth is equal to 20 voltage per meter. So finally Q is equal to 1.6 into 10 to the power of minus 5 meter cube per second. This is the flow rate. Now we are moving to the time to dewater. How much time it took for this dewatering, assuming we want to lower water table by 3 meters. They are not mentioned in practical scenario, we will calculate. Otherwise, according to the how much lower water table is required, we will do for that. Now the volume to be removed, that is equal to volume which is removed, that is equal to removable volume is equal to area into lowering. So that is equal to 20 into 20 into 3, that is equal to 1200 meter cube. So now how much time? So we are removing this much volume for where we are required that lower water table. So that is 3 meters we assume. It may 2 meters, 1 meter, 4 meters, it depends upon the scenario. So now how much time is required, that is equal to time is equal to how much we are going to remove, that is equal to V. So that is equal to how much we are removed, that is equal to 1200 divided by what are the time required, that is equal to finally we will get the 168 days. So we are removing the excess thing. So here what we understand is the how much time is required for that, and also how much volume is required. How much volume we are going to remove, it depends upon the parameters. Now we are going to do so according to that how much volume and the time required, we are finding the how many number of days is required for that. So it is nothing but the 7.5 into 10 to the power of 7 seconds converted into days. That is equal to 868 days. So these are the things which we are going to understand. So now move on to the another kind of well point system in sandy soils. So it may vary. Well point systems for clayey soils, sandy soils, where it is effective, these technique we are choosing that thing. So now this problem statement, design a well point dewatering system for sandy soils with a permeability K 5 into 10 to the power of minus 4 meters per second. The area to be dewatered is 500 meters to a depth of 2 meters. So here first we are going to determine the flow rate. So here what they mentioned, that is equal to lower the groundwater table, that is 2 meters. Area to be dewatered, how much area to be dewatered is equal to 500 meters square. Permeability of the soil is mentioned, that particular sandy soil, how much permeability is mentioned. Here Q is equal to, we know the formula, Q is equal to permeability of the soil, area, and also how much change of the lowering level and also depth of the flow path. So here K is equal to 5 into 10 to the power of minus 4. Area to be dewatered is equal to 500 meters. And how much the depth is 2 meters. And also depth of the water flow is equal to 2. So finally we will get, after doing the calculation, 0.25 meters cube per second is for the our flow rate. So this is the flow rate which we are going to understand. Now in this, how many number of walls is required? Already we observed this. So assume each wall can handle the flow rate of 0.01 meter cube per second. So now number of well points required. Required number of well points, that is equal to how much the flow rate divided by the each well point handled flow rate, that is nothing but the 25. So here in this particular case 25 well points are required for getting the desired properties of the soil to achieve the respective outcomes of that particular project. And also we will see another kind of problem statement, that is design a sump pump. So design a sump pump system, it is a technique. This is a technique. System for a construction site with a water inflow rate of 0.05 meter cube per second. So water inflow rate is equal to 0.05 meter cube per second. This is the given data. The water needs to be pumped to a height of 8 meters. So it requires 8 meters height. Determine the how much power required if the pump efficiency is 75%. If the efficiency of the pump is 75%. What we are going to do here, determine the hydraulic power. First we are going to determine the hydraulic power and determine the actual power according to that. Actual power, these are the things which we are going to know. So here the part of hydraulic power, that is nothing but the density GQH. Rho GQH is the formula for the hydraulic power. Now rho is equal to 1000 kg per meter cube in water condition. Now G is equal to 9.81 meter per second square. Q is equal to 0.05 meter cube per second. H is equal to 8 meters. So these are the parameters which we are there. As per the formula, we are finding the hydraulic power, that is equal to 31924. After calculations, we are getting the 3924 volts, the hydraulic power. Now move on to the actual power. Actual power, it is depends upon the efficiency. Efficiency is equal to hydraulic power by, this is the actual formula. So efficiency, efficiency is equal to hydraulic power divided by actual. So according to this, we are going to find out the, as per the requirement, if they mentioned, already they mentioned regarding this 75 efficiency. Now efficiency is equal to 75 efficiency already they mentioned, that is equal to 75. 0.75 is equal to hydraulic power. Hydraulic power already we derived from the equation what we know from the given data. So according to that is equal to 3924 volts divided by actual power. So now we require this actual power and we are doing the calculations. It is nothing but 5.23 kilowatts. So we calculated in terms of what? We are going to change into the kilowatts, that is equal to 5.23 kilowatts. Like this we are understanding this sump pump. So we are pumping as per the pumping efficiency. We are going to do the based on the how much power is required and how the that power is going to convert to into the pump efficiency. Based on these parameters we are going to understand this problem statement. Now move on to the another kind of hydro problem, that is horizontal well system to dewater a construction site of 2000 meters square. So the area is equal to 2000 meters square with a water flow rate of, the flow rate is equal to 0.1 meter cube per second. And also the permeability of the soil is mentioned, that is equal to 5 into 10 to the power of minus 5 meters per second. The lower water table is equal to 2 meters. So according to this, we are going to find out the required flow rate, that is equal to 0.1 meter cube per the second. How many number of horizontal walls are required? We are going to assume the each wall is going to adopt or it is going to bear the each wall. We are going to consider 0.02 meter cube per second for getting the required properties. So for this, number of horizontal walls is equal to actual flow rate is equal to 0.1 meter cube per second. This each horizontal wall is going to handle the 0.02 meter cube per second. So that n is equal to 0.1 by 0.02, that is equal to 5. So it requires 5 number of horizontal walls. These are the problem statement. For this we are going to understand what kind of soil properties are going to change. So in this one more design we are going to understand, that is equal to vacuum assisted well point system. So in this same permeability we are consider, that is equal to 1 into 10 to the power of minus 4. It may vary, depends upon the site conditions of that particular soil. The area to be dewatered is equal to 2500 meters square. In that, water table needs to lower by 3 meters. Here, according to this, using this Darcy's formula, we are going to find out the flow rate. And again, we are assuming how much vacuum assisted well point, as similar as vertical well as well as the horizontal well. Here also vacuum assisted well also we are going to how much each well is equal to how much flow rate is going to handle. So according to that we are identify the number of well points as like as the horizontal well point. So here also that is the same thing, based on the how much flow rate, actual flow rate and handle flow rate of each well point. So that from this 17 number of well points are going to are required for handling this. These are the things we are going to understand in this. And also one more, effectiveness of the electrokinetic soil stabilization. Here the site area is equal to 50 into 50. Here also the electrokinetic permeability. We already understand these kind of problem in previous. So here what we understand for this time to stabilize is, time is equal to how much water which we are going to divide it by the discharge. It is going to converted into the number of days. So these kind of flow rate issue already we see in this previous slide. So for that, first we are going to calculate the volume of the soil, flow rate, and how much time is to stabilize that particular, getting the required effectiveness of the site condition. So one more also, it is also, previous one is electrokinetic soil stabilization. This is electro-osmosis system. So we are used electro-osmosis system to dewater for the fine-grained soiled area at the depth of 3 meters. The electro-osmotic permeability So we are going to apply the voltage gradient is 2.5 voltage per meter. So here volume of water to be removed we calculated, flow rate, how much time to dewater. So the same procedure we follow for this also. And one more is evaluate the time required to dewater 60 into 60 silty soils. Here also we are going to find out the volume of the water to be required, flow rate and time to dewater. These are the steps which we follow for this kind of problem statement also using the electrodynamic dewatering. We will see few more practical solutions in our next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.